So you're making the jump from something like Arduino to an STM32 microcontroller. It's a pretty common step up, right? You're expecting all this new power, but instead you just hit a wall of complexity. Well, let's get into why that happens and, probably more importantly, how you can start thinking like an engineer to really get over that wall.
This moment. We've all been there. I mean, every single developer hits this. Everything looks perfect on your screen, the code compiles with 0 errors, you flash it, and you get nothing. Just silence. The LED doesn't blink, the serial port is dead. It feels like you've failed, but what's really happening is you've just been properly introduced to the world of embedded systems.
Okay, so here's how we're going to break this down. We'll start with that nothing works feeling, and then dig into why your hardware is the silent partner you absolutely have to pay attention to. We'll look at the tools that are meant to help but can sometimes be a trap, then we'll get into the fun stuff, the invisible enemies like timing and actual bugs in the silicon, and finally, we'll talk about the mindset shift that really changes the game and how you can move forward from here.
First things first, if you're feeling totally overwhelmed by all this, you're not alone. Seriously, the jump from a super simplified world like Arduino to the professional-grade STM32 ecosystem is, well, it's notoriously steep. You've got documentation scattered across literally thousands of pages, the tools can feel clunky, and problems that used to be easy are now these huge roadblocks. This is not a personal failure, it's just the nature of the beast.
You know, the biggest mental gear you have to shift for embedded development is this. Your software is not just floating in the ether. Every single line of code you write is physically poking and prodding a piece of silicon. Let's look at a super simple example of what I mean. So let's say you're trying to debug your project, and you write this line. You see it? You used single quotes instead of double quotes for a string. On your PC, this might just spit out a weird number or maybe a compiler warning, but on an STM32, you get nothing. Crickets. So you fix the quotes, flash it again, and still nothing happens.
It really feels like it should be, doesn't it? Just a simple syntax error. But in the embedded world, oh man, the answer is so much bigger than that. The reason it's failing has almost nothing to do with C syntax.
This right here is the hidden iceberg. For that one little printf to actually work, a whole chain of hardware has to be perfectly set up by you. You have to go into the reset and clock control, the RCC, and turn on the clock for the right peripheral. You have to take some of your general-purpose input-output pins, your GPIOs, and tell them, hey, you're not a simple pin anymore, you're now a UART transmitter. Then you have to configure that UART peripheral itself, the baud rate, all that stuff. And of course, you actually need a physical wire connecting it to your computer. That typo wasn't the real problem. It was just a tiny distraction from a much bigger hardware setup issue.
And this really gets at the heart of why STM32s are so complex. They're not just microcontrollers, they're systems on chip, or SoCs. The best way to think about it is like an entire computer motherboard from the 90s, with a CPU, memory, timers, communication chips all crammed onto one tiny piece of silicon. Now this is incredibly powerful, but all those different parts, all running on their own clocks, have to be stitched together. And that stitching, that interconnection, is where so many of our headaches with timing and documentation come from.
Okay, so if it's that complex, how is anyone supposed to manage it all? Well, ST gives you tools to help, of course, but these tools come with their own set of trade-offs, and they can become a trap of their own if you're not careful.
So this is really the core dilemma in STM32 development. You've got 3 ways to talk to the hardware. Way down at the bottom, you can just write directly to the hardware registers. It's as fast as you can possibly get, smallest code size, but the learning curve is a vertical wall, and your code won't work on any other chip. To make life easier, ST gives us the how, the hardware abstraction layer. It's easy to learn, it's portable, but the price you pay is huge, your code gets bigger, it runs slower, and it hides all the details of what's really happening underneath. And somewhere in the middle are the LL, or low-layer libraries, which are kind of a compromise.
And hey, don't just take my word for it. This quote from the community just nails the frustration with the HAL. It's built to be safe, so it has tons of internal checks. But when one of those checks fails, it often just dumps your program into a silent, infinite loop with no clue as to what went wrong. For a beginner, this is just one more way for your board to turn into that unresponsive brick.
This is the key takeaway here. Most pros don't just pick one and stick with it. They use a smart, hybrid approach. They might use a graphical tool like STM32CubeMX in the HAL to get all the boring initial setup code done for clocks and simple stuff. But when they get to a part of their code that needs to be fast and precise, like handling high-speed data, they'll drop down to the low-layer libraries or even write directly to the registers to get the performance and control they absolutely need.
All right, now we're getting into the stuff that really separates day-to-day coding from professional engineering. We're talking about the invisible enemies, the problems you will never find just by staring at your own code. This is a classic textbook trap
The HAL gives you this handy little function, HAL delay. Super simple, but under the hood, it works by waiting on a system timer called the sysTick, which fires its own interrupt every millisecond to tick a counter. Now here's the trap. What if you call HAL delay from inside another interrupt? Let's say your UART interrupt. If your UART interrupt has a higher priority than the sysTick interrupt, and it often does, you've just created a deadlock. Your code is now stuck, waiting for a timer that can never tick, because the interrupt that ticks it is a lower priority and can never break in. The whole system just freezes, solid.
Now here's a concept that'll really bend your brain. When you're debugging code on your computer, you hit a breakpoint, and the whole world stops. Simple. In an embedded system, that is not true at all. You can hit a breakpoint and stop the CPU core dead in its tracks. But guess what? The peripherals, the timers, the communication ports, the DMA, they can just keep on running in the background. This means the very act of looking at your system changes how it behaves. You might pause to check a variable, but while you're paused, a hardware timer overflows, and that creates a brand new bug that only exists because you were debugging.
And for the final dose of reality, and this is probably the most humbling one, the hardware itself can be wrong. Every single chip ships with a document called an errata sheet. That's just a polite word for a list of bugs we found in the silicon. These aren't software bugs, they are physical flaws in the chip. You might find out that writing 1 byte to the SPI port actually sends 2, or that a pin that's supposed to be 5-volt tolerant isn't when the chip is powered off. It means your code has to be smart enough to work around the physical flaws of the very thing it's running.
So with all of this, how on earth does anybody get anything done? Well, the answer isn't about memorizing every single hardware register. It's about a fundamental shift in how you think. It's about going from being just a coder to being a systems engineer.
Here's the difference. A coder asks, does my code compile? An engineer asks, is the entire system in a known, predictable state? A coder thinks, the bug must be in my logic. An engineer knows the bug could be anywhere. In their code, sure, but it could also be in the vendor's HAL library, the clock setup, the physical wiring on the board, or even in the silicon itself. And the big one. For a coder, the datasheet is that scary 1,000-page PDF you only open when you're desperate. For an engineer, the datasheet is the Bible. It is the source of truth.
This mindset leads to real-world habits. You learn to read the silicon, to actually understand the chip's physical limits right from the datasheet. You learn to debug the physics. You realize that when your I2C bus isn't working, the answer is probably on an oscilloscope screen, not in your code debugger. You learn to manage the overhead, to know exactly what that convenient HAL function is costing you. And maybe most important of all, you learn to expect failure. You build code that's tough enough to handle hardware that misbehaves.
So where do you go from here? Look, I know this can sound a bit intimidating, but just understanding what you're up against is the single biggest step toward conquering it.
You've got to reframe how you see this stuff. Every hour you spend chasing down some bug that turns out to be a flaky solder joint or a misconfigured clock, that's not wasted time. That is a hard-won lesson about the fundamentals of your system that is now burned into your brain forever. That's how you build real, deep, practical knowledge.
No one expects you to memorize a 2,000-page reference manual before you write Hello World. That's not the point. The point is to build the habit of checking it, of being patient, of being methodical, and approaching every single problem with a genuine curiosity about the entire system, from silicon all the way up to your code.
And that's really what it all boils down to. This journey into the world of STM32 is tough because it demands that you become more than just a programmer. It forces you to become an engineer who really gets that intricate dance between software and hardware. So the next time your board is a brick and you're just staring at code that looks absolutely perfect, ask yourself that question. Your answer is what's going to define your path forward.
If you like this one, the YouTube algorithm says you're going to love my other videos, so go check them out.